So the additivity property is one of our most used properties, and it's unique to definite integrals. This is the property that allows us to take a definite integral and break it into pieces, or to take the pieces and put them back together into one integral. So the idea of it is, again, I'm just going to use a number line to illustrate this. Oops, sorry about that. So if I have a number line, I could say that I want to start at A and go all the way to B. Or I could say I want to start at A and go to C, then from C to B. And it's going to give me the exact same thing as if I go from A to B. Several things that we have to watch for. When we look at this, the integrands are all the same. What we're taking the integral of doesn't change. It's the bounds that are changing. We're taking it and saying, even though I'm looking at the same thing, I'm going to break it into pieces and just focus on piece bit by bit. The second thing we need to look at is noticing my bounds. So noticing that the lower bound of one integral is the same as the upper bound of the other integral. And then the third thing, I have to be adding the integrals. It has to be addition. If it's subtraction, this doesn't work. Because that's what we're doing, is we're saying, I want to break it into pieces, find the area of each piece, and add them back together, get the area of the whole thing. So when I look at this, what I'm looking for is each of those things. So I notice, so I have the integral from -1 to 1 of f plus the integral from 1 to 4 of f. Integrands are the same. That's good. I can see the lower bound of one is the upper bound of the other. And I'm adding. So I'm finding an integral of f of x with respect to x, but it says I'm going from -1 to 1 and then from 1 to 4. Well, I can just go -1 to 4. So then if I look at example 2, again, I'm noticing integrands are the same. Oh, but now I start running into problems. I'm noticing that's not addition. And I'm noticing that the -1s are the same, but they're both lower bounds. Well, this is where one of the other properties I can use comes in, which is the order of integration property. If I keep my first integral the same, and I change the order of the bounds on the second one, so 3 becomes the lower bound, -1 is now the upper bound, it changes the sign because I changed directions, and that becomes a plus. Well, now I've met the conditions for additivity, and I can say this is the integral from 3 to 7 of f of x with respect to x. Oops. Sorry. So now where this gets more complicated, or where the way they typically check these is they give you kind of problems where you don't know what f or g or h is, and they just say, hey, go ahead and take these kind of generic values for definite integrals and see if you can find other definite integral values from them. So if you want a little bit of a challenge, pause the video here, and try them on your own and then play the video to see if you got them right, or kind of work along with me here. So if I want to know the integral from 4 to 1 of f, well, 4 to 1 is kind of awkward. It'd be nice if I changed that using the order of integration to be 1 to 4. Well, they tell me the integral from 1 to 4 for f is 7, so I get -7. If I want the integral from -1 to 4, well, I know I have the integral from -1 to 1 and from 1 to 4, so I can use additivity there and say, well, let me break it up into those two that I'm adding together, which would be -2 plus 7, which is 5. For -1 to 1 of 2 f of x plus 3 h of x, I actually have several properties here. I have the sum and difference property because I can break that up, and I have the constant multiples, so I can pull the 2 out. So I have 2 times the integral of -1 to 1 of f with respect to x plus 3 times the integral from -1 to 1 of h with respect to x, which will be 2 times -2 plus 3 times 5, which is 11. And then the integral from -1 to 1 of f of u du is actually going to be exactly the same as if that was an x. It's -1 to 1 of f of x with respect to x. Because the name of the variable wouldn't change what the graph would look like. It would still be the exact same looking graph, which gives me the exact same areas. So -2.